Now, if you put a lot of fresh water into regions of the ocean where you have significant downwelling due to the water being salty and cold and sinking, you see two little yellow points up at the top here of this nice image of the linked global circulation of the oceans. I should just back off a little bit and say that Carl Wunsch or others who are kind of real oceanographers will point out to you that there's 10 times as much energy in the little kinetic whirls of the ocean, so that they feel that this rather underrepresents the way the ocean really works. But nevertheless, there are systematic drifts in the ocean, and this picture does bear some relationship to the way that the real ocean works. And what you can see is that if we just concentrate on the north for the moment, there are some key points in this system which, if you tamper with them, can have global consequences. And we know that in the last glacial period, it's postulated sudden rushes of fresh water into this northern area changed the downwelling and therefore the global circulation of the oceans. We don't know if this can happen in warm periods, the interglacial that we're in now, but clearly there's a concern if we've got increased melting, changes in the behavior of Arctic sea ice, that this may happen. And NERC has responded to this with its RAPID program, where we're both through measurements and also comparison with models, trying to figure out whether there will be a regime shift from the left panel to the right panel with a major impact on regional climate to the east of this zone and on fisheries and indeed the whole ocean ecosystem in this area. So another big reason to worry about changes in the north. Down in the south, this is a year-long animation, an animation of a year's worth, you don't have to sit here for a year, of Antarctic sea ice melting away in the summer and then regrowing again in the winter. So this is built up from daily satellite composites. This is the biggest physical dynamic change on the Earth's surface over the year, the doubling of the size of this white blob on the bottom of the planet. Of course, the sea ice isn't very thick, it's fairly fragile. As yet, there's no evidence of the bulk of the sea ice melting back in the same way that it is in the Arctic. But in the Bellingshausen Sea, why didn't that work? There we are. In this area in the purple circle, there has been a significant reduction of sea ice, possibly not so much by melting, but by a change in the prevailing winds that pushes it a bit further south. And this is linked, or seen to be linked, with the strong warming that you saw in that earlier Hansen plot of warming over the Antarctic Peninsula, although there are other mechanisms which are gradually being understood which account for that warming too. Now, this sea ice, again, provides this insulating cap between the ocean and the atmosphere. What I forgot to mention in the case of the Arctic, but it's particularly important in the case of the Antarctic, is that this provides a substrate for biological activity, particularly for krill, and I'm going to come on to that in the next slide. This little fellow, and you can see the green plants that he's been eating in his gut there. So he grazes on phytoplankton, which in the spring grow like upturned meadows under the sea ice. And krill is the substrate of is the main substrate of the Southern Ocean ecosystem. So biologists argue that this is a fairly simple, relatively simple ecosystem. If you can understand this, you're doing fine. This is a good one to model. The complication is that ecosystem, which is biologically fairly simple, not that many trophic levels in it, is being transported by this strong circumpolar current, the Antarctic circumpolar current. And so krill that spawn under the sea ice around the peninsula, which is being affected by this strong regional warming, are carried by this conveyor belt round to the kind of Serengeti of the Southern Ocean, which is around South Georgia and to the east of it, where one has this huge intensity of seals, penguins, albatrosses, fish, all of the high predators. Now, what we know is that there are teleconnections, both ocean and atmospheric teleconnections, from the equatorial Pacific to the sea ice around the peninsula. And a couple of years after a major El Nino event, the sea ice is reduced. That causes a reduction in the supply of krill. That information takes a little while to make its way across to the South Georgia breeding area. But when that lack of krill reaches there, all of these guys have a bad year. And you can see the curves showing breeding success of 4 higher predators. So what we know is that, if you like, 4 to 7 yearly natural cycles with teleconnections can have huge impacts on the breeding success of this Serengeti. And so, of course, one's concerned about what the secular change effect will be as this area warms further. And it's not just, if you like, a biodiversity argument or an argument about preserving the planet the way we found it, but there's a very major and economic fishery in this area, which is managed using an ecosystem approach, but clearly there are livelihoods that depend on the breeding success of the fish in this area and indeed the health of the whole ecosystem. So this isn't just an academic issue. There are strong commercial interests in understanding how this system functions too. Right, so I've been talking about regional effects of regional warming in the polar regions, so sea ice reduction and the consequences of that, possible changes to ocean circulation and related changes to climate because the ocean and the atmosphere are so tightly coupled, ecosystem impacts, fisheries impacts in particular. Now, I just want to go on to a little bit further. The warming in the peninsula is very dramatic. We have the temperature records, but we see the consequences. A study last year showed that 400 mountain glaciers along the Antarctic Peninsula, 75, roughly 80% are in retreat. Some new work, which will be published shortly, will provide some very interesting new results on the extent to which they have also accelerated their discharge and therefore increased their contribution to global mean sea level rise. And the bottom line is that it's significant. We've also seen the collapse of a number of ice shelves, much heralded in the newspapers. This is something that the media and public are very interested in. So the red stars show where ice shelves have collapsed. The green stars show where ice shelves are still in place. The beige line shows roughly what we can describe as the 0-degree summer isotherm. So at present, to the north of that, one gets significant summer melting, surface melting. To the south of it, one essentially doesn't. And the physics behind these collapses, it's all to do with the effect of surface meltwater leveraging the collapse of the ice shelves by seeping down through cracks and essentially breaking up the mechanical or weakening the mechanical fabric so that some other event, maybe a storm, maybe some sort of ocean surge, can cause them to catastrophically collapse. And the point about it is that over the last 50 years, that beige line has moved further and further south. It has to go a long way. We have to have a very substantial warming before we get anywhere near the major ice shelves of the Ronnie Filchner. And that's an important point to make. The bulk of the Antarctic ice is well below 0 degrees centigrade and so is still, if you like, secure and safe.